Hello student, I am Jvn Dr. Kumar Srivastava from the Department of Science under the Faculty of Education and Technology, Jvn Dr. University, Jaipur. Today I will discuss integral domain. Today I will discuss integral domain and some related theorem. The theorem is every finite integral domain is a field. From the early videos, we have studied about the definition of integral domain and field. Now we have to prove every finite integral domain is a field. Proof. Let t comma plus comma dot be a finite integral domain so that it means d comma plus is an abelian. D comma dot is a stupid group. D has unity. D is commutative. D has no zero divisor. The two distributive law holds in D. It means D comma plus comma dot is a finite integral domain. We have to prove D is a field. From the property phi, D is field. From the property phi, D has no proper zero divisor. Cancellation law holds in D. Since D is finite and hence D contains a finite number, say n of element. Let these elements be x1, x2, x3, and so on xn. That is x1, x2, x3, and so on xn. Any element A is arbitrary such that A is not 0. Then ax1, ax2, ax3, and so on axn belongs to B. Therefore, the same n elements x1, x2, and so on xn, but in different order, xi, xj belongs to j, d, such that axi is equal to axj, axi is equal to axj. That implies a in bracket xi minus xj is equal to 0. Since d is free from the zero divisor, that implies xi minus xj is equal to 0. That implies xi is equal to xj. Thus, we have proved axi is equal to axj. That implies xi is equal to xj. Or equivalently, xi is not equal to xj. That implies axi is not equal to axj. Hence, axi, x1, ax2, and so on axn belongs to T are distinct elements. D contains unity elements, that implies 1 belongs to D, that implies there exists an element AXP belongs to D such that AXP is equal to 1, but D contains the unit elements. That implies AXP is equal to XPA is equal to 1. That implies A inverse is equal to XP, XP belongs to D. That implies A inverse belongs to D. That implies A has the multiple identity D. Thus, we have shown that every non-zero element of D has multiplication inverse in D. That implies D is a field. Thank you.